So we've been discussing graph and some of the properties of the graph and different terminologies to describe a graph, different term vertices, edges, and stuff like that. And we just get too familiar with those terminologies, and we try to cover very, very basic properties of each. Things like paths, the sequence of vertices in a graph, if you wanted to find the path in it. And there's something like simple path. What was a simple path again? What was a simple path again? 아이고. Paths that all the vertices are different, right? Except maybe the first and last one. So we did take a look at some of the path examples and simple path examples. We'll also start discussing like you can start giving a value on top of edges. So it's sometimes called it as a weight, or more familiar term to us is a cost, right? Once you start having a cost in your graph, then naturally it asks you to find a path with a sometimes a minimum cost or a maximum cost. Depends on the problems, right? Basically, the definition was length of the path is the sum of the lengths of the edge on the path. So you just add up all the costs in your path, right? The things that we know from some of the stuff from a Introduction to Computer Science last term, when we covered a shortest path discovering algorithms such as Dijkstra, stuff like that, right? We know the basics of it. 맞지? Too early in the morning? Too early in the morning? But 9 is not too early in the morning. 나 오다가 차가 너무 많이 막혀서 늦는 줄 알았어요. 처음으로 지각을 하나 간당간당 했는데 다행히. So like this morning there was too much traffic, so there was no minimum cost path. All the path was really, really bad. I could not find any other alternative path to this traffic maps that we have. Right. Subgraph and cycles. Subgraph is actually part of graph. All the edges and vertices is a part of an entire graph, right? That was definition. And cycle was also mentioned. Basically, if you encounter the node that is already been visited in your past, then it's a cycle, and naturally the problem later goes to whether it's a given graph has a cycle or not. That's important, especially if you go into graph searching problems. Some graph with the cycles, some algorithms for searching a node in your graph will not work. So preconditions for those such problems usually ask for non-cycle, no cycle within the graph, then your algorithm will work. Those things, preconditions are usually given in certain problems, and so on and so on. If you guys take a look at the graph section of your textbook, a little bit. So it's compared to the other chapters, it's more of an introductory. I mean, basically give you very simple graph examples, and this is path, this is subgraph, this is connected. That's it. They didn't discuss too much of the complex problems in those chapters. So, like I say, we just try to cover really, really basic. So later, some of you might go into continue on this topic later. So I just wanted to give you some very, very basic ideas on it. Okay, what was spanning tree? Spanning tree, a connected undirected graph that contains a no cycle is a tree, right? So it's pretty much all the trees are spanning tree. It's a spanning tree. Everything is connected. Everything is connected. Spanning tree has n vertices and n-1 edges. When I was explaining this property, I was drawing like this. I usually look at this and think of this. N vertices, 1, 2, 3, 4, 5, 6. 6 vertices, and there is a line between them, so 5 edges. So that's, I usually remember this properties, like spanning tree has n vertices and n minus 1 edges. Important thing is, everything is connected. From one node to every other node, there is a path. You can get there. If you delete any one of these any one of these edges anywhere, the graph would not be connected. You cannot go to somewhere else. That was an important property of the spanning tree. These are the simple example. I also ask you to take a look at the books, and they actually give you this type of stuff, and they actually give you this bold line as one of the example for minimum cost spanning tree, this bold lines. This is entire graph. If you just connect these bold lines, then it's a tree, spanning tree that connect everyone. I think that is also a minimum cost spanning tree. Last week someone asked whether there is only one spanning tree. I think you asked me whether there is only one spanning tree. No, it's not unique. There may be multiple spanning tree in your graph, but you can choose one with the minimum cost if that's what you're looking for. So that was it. I think we're around here and kind of stop. Bipartite graph. Also, different type of graph, mentioning that simply you can divide it into two different sections. They try to describe in a bit more complex way, disjoint sets and U and V. Simply means if you can divide all the vertices in two different groups, and within the groups, if there's no edges among them, and you only have edges to vertices on another group, then it's a bipartite graph. So sometimes some questions, they give a very complex looking graph and ask you, find out whether this given graph is bipartite graph or not. Questions like that exist. 어쩔 때는 그런 질문들도 있을 수 있어요. 우리는 뭐 커버를 많이 안 하지만 좀 복잡해 보이는 그래프를 딱 갖다 주고 이 그래프가 바이파르타의 그래프인지 아닌지 증명해라. 그런 식으로 물어보는 경우도 있어요. What if I ask you to write out a program that can determine whether some of your graph is bipartite or not? Well, it might be challenging for some of us. Even for me, I don't know how to write it. I have to think about the algorithms. But first step, probably look at the properties of each, right? What might be the dumbest way that you can write this program? Finding out bipartite graph. I don't know, I haven't looked it up. There must be really nice algorithms. But what might be the dumbest way of writing this program? Find out whether your given graph is bipartite graph or not. 정말 멍청하게 쓰면 어떻게 짤 수 있을까? pseudocode. Any ideas? Any suggestions? 나도 안 찾아보고 왔어. I don't know. There may be. I think there exist such algorithms, but at this moment, 뭐가 있을까? You select random set of vertices and test every single time. Test every single combination. Test every single sets. And then if one of them satisfies this condition, then you can say it's bipartite. Of course, it would be dumb algorithms. They have to try everything. It's something like greedy algorithms. They try every possibilities. So that might be one approach. Otherwise, I don't know. 예를 들어 랜덤 노드 하나 잡아서 가보고 그런 식으로 계속 랜덤 노드 잡아서 하다가 겹치는 그룹이 나오면 속된 말로 나가리. 이런 식으로 테스트하는 반복적으로 해본다든가. 분명히 더 좋은 알고리즘이 있을 건데 기억이 안 납니다. 하도 오래돼서. 찾아봐서 한번 해봐요. So that might be a very good exercise for your programming skills. Of course, like I say last class, you have to first decide on how to represent this graph on your data structures in your programs, right? There was a couple of approaches we briefly looked at, right? 뭐였지? Of course, you can basically think of arrays and chain linked list, right? I think I draw something like matrices. We will cover that today as well. Yeah, this one we also covered. It's quite obvious on directed graph how many number of edges in that graph. Maximum number of edges that you can have is n node, n times n minus 1 divided by 2 because there's no direction in it. 그지? N times n minus 1 means that there is an edges between from one node to every other node. Likewise, for the directed graph, because there's a directional stuff, the number of edges that they can have is n times n minus 1 because it has both directions in it. You don't have to divide by 2. That was properties. And then we start looking at the vertex degrees. Simply, as we know, as a node degree is how many edges that you encounter in your node. You just simply count that. Example was like node 2 in this graph has degree 2, 그죠? Two lines coming in and out of node 2. Likewise, degree 5 is no degree of node 5. Well, 3. Likewise. So if you add them up, sum of the degrees will be equal to 2 times number of edges. 그치? Because you're counting the edges twice from single node. Because one edge share 2 vertices. So if you count from single side, then it's naturally 2 times all number of edges. If you add them all the number of degrees in your vertices. 이거 말 되지? 이거 뻔하지? What if it's a directional graph? directional 아니다. No, not forget about directional. Yes, it is directional. I think we covered that much. I bring a concept for something else. Now they try to divide the node degree into 2 different definitions. Things like in degree and out degree. This is cases for directed. In and out. Obviously, it depends on the direction of your edges. So, in degree of vertex I is a number of edges incident to I. What was the incident? If you share edges in a node, then you usually call edge I is incident edge. That edge is incident to the node that is attached to. Those were the term to describe that you have edges from your node. So number of incoming edges. So from vertices point of view, how many edges that is coming to me in degree. Likewise, the out degree, how many edges going out from me, right? So in degree of node 2 is, well, 2, only 1 edges coming into 2. 1. In degree of 8. 눈이 안 보인다. In degree of 8 is what? Because no edges is pointing to node 8, right? In the out degree of 8, probably just 1, because 8 is pointing to 9 in that example. So in degree, out degree is another property that describes for the directed graph, directed edges in it. Sum of the degree, it says 2 times all the number of edges, because you're counting this edges twice, because one from 10, one from 11. 맞지? 2 times E number of edges. unlike the directional graph, you're not counting 2 because they divide into in degree and out degrees, right? 생각해보면 되게 단순한 건데 순간 수업에서 넘어가니까 금방 헷갈릴 수도 있어요. 되게 단순한 건데. So that's the part. I mean, because in directional graph you divide it into in degree and out degree. So some of the in degrees, some of the out degrees will be equal to number of edges, right? This one was a no degree of unidirectional graph is 2 times e. So that was the sum of the degrees in unidirectional graph and some of the in degree out degrees of a directed graph, right? So these are the problems look like. Most of the graph relating problems asking you these stuff, whether you have a certain path in it in your graph. So that's a path finding problem. This is also similar to another way of saying is you're looking for a node in the graph. You're looking for a particular node in the graph. Like the examples that we saw from binary search trees that all the things that we try to do is we're looking for a node with a certain value in it, right? If we find the value, if we add it, if we can delete it, and all kind of operation will be done on top of it. So while you're finding that particular node, you have to go through certain path in the binary search tree. So those two problems are related. And second problem, they usually ask for connectedness problems, whether some part of the subgraph is connected or not. Or usually they give you connected graph and ask you to which edges can be removed so your graph is no longer to be connected. So you're looking for something called bridge edges in it. And the third is spanning tree problems. Spanning tree problems. Given the graph, they ask you to find a spanning trees. One spanning trees finding algorithm that we all might know is Dijkstra for finding shortest path algorithms. That particular problem, we try to find every path from one node to every other node, right? If you connect those stuff, then you have one example for spanning tree. Not so sure that will be the minimum spanning tree, but that's the one way that we already know. It's kindergarten stuff. It's just finding a path, following by the fingers, and you can find the path from 1 to 8. There's one thing I don't like this. I don't like, there's one thing that I don't like here in your textbooks. This graph chapter is a bit dumb. 약간 너무 기본만 한 것 같아서. Or example of no path. Path from 2 to 9. How do you find out there's no path from one node to one other node? How do you find out there's no path? Right. Maybe you need to modify your path searching algorithm or spanning tree algorithm that you find the point that some node is not covered in your algorithm, then you should print out the messages like false, your graph is not connected or something like that. That might be one approach that you can modify the existing path finding algorithm to find out if there's some edges, some nodes are not connected. Likewise, connected graph, let G, V, E, that we know. So next time we meet each other somewhere else, then if I ask you to give me a graph definition, I hope you guys can give me that. G equal to V, set of V and E, right? G is connected if and only if there's a path between every pair of the vertices in G. It's the same thing that I'm saying, there exists all the paths from one node to every other node. If so, that is a connected graph. Likewise, it's the same thing. So they're going to say it's a G is connected if and only if there's a path between every pair in the vertices in G. If not, it's not connected. obvious example is like this. 눈으로 보면 참 쉬운데 if I ask you to write a program on top of this, can you do it easily? Hopefully you have a better idea once later we saw one of the data structure example on this graph. 5 and 9, if you connected the 5 and now it's connected. Although the textbook didn't mention about this edge is usually called something called bridge. bridge라고도 많이 얘기하기도 해요. bridge. Because those are the bridge actually from one subgraph to another subgraph, right? Connected component is a maximal subgraph that is connected. It's not that important. I'm gonna skip. This is all the part of this stuff. 미안, 그 두 개는 넘어가도 될 것 같아. Like I mentioned last class, that this graph problem usually translate into a networking problem. Networking problem, if you're not so sure what's a network, then it's more of an internet problem. If you try to map the internet, and usually if you abstract all the things in the between, then usually work with this type of graph in order to find out the path in the internet. There used to be a very famous interview questions like, how do you find out the diameter of a internet? I think it was one of the interview questions, Google이었나? Probably Google or Microsoft. They ask you to answer that question, I think the question is more like, how do you, please give me a pseudocode of finding the diameter of the internet. How would you respond to that? 어떻게 해야 돼? 똑같이. So maybe good idea, I don't know the exact answer, but good idea might be think of this graph like this in your brain and maybe start building an algorithm on top of it. Otherwise, you don't have any abstractions in it, so it's hard to think, hard to begin where to start, hard to find out where to start. 그지? 그 진짜 실제 그 인터뷰 요즘엔 그것도 너무 많이 알려진 질문이라 물어보지도 않을 거고. 인터넷에 지름이라고 그래야 되나? 지름을 구하라 이렇게 얘기했대요. 그럼 어디서부터 시작을 해야 돼? 지름을 어떻게 구해? 지름 구하는 알고리즘. 지름이 얼마냐고 물어보면 어떻게 구할 거냐고 물어보면 어떻게 해? 그렇게 버벅대면 끝나는 겁니다. 이제. 뭐 정답이 하나가 딱 있지는 않겠지. 그러니까 첫 번째 머릿속에 떠올려야 될 게 이런 식의 그래프가 되겠죠. 이런 식의 그래프를 떠올려 놓고 뭐 그냥 막 갖다 붙이는 거지. shortest path 알고리즘 자기가 아는 거 막 얘기하면서 그런 알고리즘을 중간중간에 섞어가면서 하면 최소한의 길이가 나오지 않겠습니까? 뭐 어떻게 뭐 이러면 내가 한쪽한테 인터넷으로 메시지를 보낼 때 걸리는 시간을 재서 그거를 거리로 뭐 빛의 속도는 다 뻔히 나오니까 빛의 속도로 뭐 반비례 갖고 하면 뭐 어느 정도 대충 나오지 않겠습니까? 이런 식으로 얼버무려야지 뭐. 그렇죠? 근데 이런 식의 그래프 띵킹을 안 하면 아예 시작할 수 있는 포인트를 알 수가 없지. 그냥 머릿속에 구름만 그리고 있으면 인터넷 구름 이렇게 되면 굉장히 답답한 상황이 나오니까. Communication network problems is if your internet having a problem, if your internet connection is not good, then you usually ask, am I connected? Am I connected to the internet okay? Usually, the first thing that you're looking for is what? If you're thinking you're having an internet problem, what is the first thing that you look for? 컴퓨터가 갑자기 자기네 쓰는 컴퓨터가 인터넷 안 되면 제일 먼저 뭘 의심해? 그치? Is everything okay with my own computer? And you find out that everything seems to be okay. You type down your password and ID okay. What is the second thing that you usually suspect? 인터넷을 안 하면 아예 그냥 연결 안 되면 안 하니까. 그죠? Usually ask yourself whether I'm being connected to a right position, whether I have my path in it, into the system. So, is there a path to my computer from the internet? Everything okay? How do you find out that you have your path okay or not? Can we communicate between every pair of the cities? Can you connect it to every other person in the internet? Yes, theoretically yes, because there seems to be many different paths to a single destination. Find the components, some part of the network that you don't go to, like subgraph that you don't care. Wanted to construct a smallest number of feasible link so the resulting network is connected. How do you translate that, construct the smallest number of feasible link in your internet connections? How do you translate that into internet language? Smallest feasible link. Usually, how fast can you download the data? Which path that you take gives you the fastest download data. Have you tried to download something on the BitTorrent lately from the campus network? Last time I think I showed you something like this in this computer. 근데 recently, I think a couple of months, just for about a month, speed really gets really fast now. 갑자기 스피드가 굉장히 빨라졌어 학교에. 뭘 한 거 같아 학교에서. 내 방에서 여기선 전에 10메가도 나왔었잖아 한번 할 때. 10메가 나왔었는데 내 방에서는 그렇게 10메가까지는 안 나왔는데 최근에 5메가까지도 막 나오기 시작하는데 아무래도 패스를 바꿨든지 돈을 내고 패스를 바꿨든지 아니면 또 뭐가 있을까? 나머지 하나가 뭘까? 웨이트 있지. 웨이트 밸류. 예를 들어 패스를 큰 걸 샀든지 그러면 웨이트 밸류 아까 커스트 밸류가 갑자기 커진 걸 샀든지 둘 중에 하나일 것 같아. 갑자기 빨라졌어. 하기야 뭐 네트워크니까. I think I explained most of the cycles and connectedness stuff. Removal of this particular edge, removal of the edge between 5 and 9 is 아니다. Removal of the edge that is on a cycle does not affect the connectedness. Yeah. If you remove a cycle in the graph, does it have an impact on the overall connectedness? Usually no. Cycle have a redundant edges in it, right? So, which edges can be removed without affecting the connectedness? Oh, that's another good question too. That's another good programming exercise to do it. Given this graph, find out the edges that is not required. Maybe it's a part of the finding spanning tree. If it's not belonging to, if some of the edges not belonging to spanning tree, then you can maybe remove. There might be one idea that you can use by reusing the spanning tree algorithms. 여기서 뭐 눈으로 보면 maybe you don't need the edges between 1 and 2 stuff. 뭐 1하고 2는 없어도 될 것 같고 some of the edges that you can remove in this way. Okay, this one is another repetition. So finally, representation of the unweighted graphs. 3 different ways: adjacent matrix, link adjacent list, array adjacent list. They say it's the most frequently used representation for unweighted graph in these examples. We covered some of that already. Adjacent matrix, like this. So now you declare a 2D array of array. How do you define 2D arrays? 이렇게 쓰지? 그치? 아니다. My graph 5 and 5. Node with the 5. So it's an n by n matrices where n is number of vertices. Aij is 1 if and only if and only if ij has an edge between them. So it's very simple representation. Node between 1 and 2, 1 and 2 has an edge, so 1. If they don't have an edge, then 0. Likewise, 2 and 1 also have edge because there is already edge. So 1, 1. 1, 1. So now you just represent this graph in this 2D matrix. Matrix is 2D. Matrix. So what seems to be a property of this matrix? Symmetric. Yeah. All the diagonals are 0 because 1, 1 is itself. And because it's undirected graph, edges are overlapping between the two. So symmetric matrix. Done. You just represent your graph into a data structure using this matrix. That's how you represent this graph. So if you want to find out the path between maybe 1 and 4, 1 to 5. I'd like to find out the path from 1 to 5. How do I do it? I don't looking at this anymore. I just look at this now. So maybe I can start from like this. My brief pseudocode will be, I'm starting from 1. So let me find out the path from 1. Okay, start from 1. Let me take a look. I can get to 2 and 4. Okay. Let's take a look at 2 first. From 2, I can get to 1 and 5. 5 is a destination that I wanted to go, right? I just find out the path from 1 to 5. 그지? Just you keep looking at the matrix until you go to the destination that you're looking for. That might be that's my very brief pseudo code for looking for path in this graph representation. Make sense? 그죠? It's not too bad. Not too bad. What if you start having a cost on top of the edges? Weights. 여기에 만약에 웨이트가 있으면 어떻게? Maybe one easy way to do it, you replace this with the weights. Maybe 1 to 2 have a 10. 1 to 4 is 5, 10, 5. Might be one way to do it. Then you can also calculate the cost between the different combination of different paths in your graph. So you don't need to take a look at that anymore. Another important point to look at when you try to implement this type of stuff, type of graph. I also take a look at it this way. If I have this, can I reconstruct my graph? Can I reconstruct my original graph? Is it easy to do or difficult to do? That's the one thing that I usually looking for when if I do this myself. 나도 그래프, 노드 한 1000개, 2000개 이런 그래프를 이렇게 옮겨야 될 경우가 있고 그랬었어요. 근데 이게 조금 커지면 좀 곤란한 게, 예를 들어 노드가 1000개야. 그 매트릭스가 사이즈가 얼마야? 1000 by 1000이죠. 1000 곱하기 1000에 1000 곱하기 1000에 패스 파인딩 알고리즘 돌리면 한참 돌아갑니다. 사이즈가 커지면 좀 다른 방법을 찾아야 될 필요도 있고 쉽지 않죠. Likewise, these just the properties that I just mentioned. Diagonal entries for this adjacent matrix properties are the diagonals are 0. Adjacent matrix of an undirected graph is symmetric. That's all we know because Aij is equal to Aji. It's the same thing. There's no direction in it. So that's the one thing that you can do. Directional graph. What if you try to use this matrix to represent a directed graph? Diagonal entry is still 0, but from one point to the other, you have zeros and ones in the right place, so it's no longer a symmetric graph. symmetric matrix, graph matrix, confused. 1 to 2, 2 to 1, 2 to 1, 1, but there's no path from 1 to 2, so 0 directions in it. So you can manipulate this matrix to do it. What about others? Adjacent list. Matrix seems there's a lot of empty space in it, so you're wasting your space, right? A lot of zeros. This is only a few ones. Usually when you try to minimize the space complexity, that you usually make a use of a linked list, right? Linked list. So this is the same thing. So in this way, you have from node 1, you have your neighbors 2 and 4. Node 2, you have neighbors of 1 and 5. So you just simply replace this. This is already an array. From array, each entry of the array, you put this 2 and 4, 1 and 5, 5 on the side. Using a linked list, maybe. That's one way to do it. Like that. I don't need to explain this anymore, right? Once we see this figure, then you know how to do it, right? You keep track of the pointers in the list and the value of this particular node, and then once you find out there's a node in the graph, you add a extra node, extra linked list, extra node, added it, and then it's a compressed way of representing your matrix, the previous matrix that we saw. Right? That's one way of doing it too. 그치? 할 수 있지? It's not so much difficult anymore. We know how to do this in the linked list anyways. 많이 해봤잖아요, so I don't need to explain that much anymore. This is linked adjacent list. What if we just simply add a list on each entry? This is same thing, but instead of the linked list, you create a list in it. List of the list again. But you can create a list of the certain size, like declare list size 2, list size 3, then you're not wasting your space like the matrix ones. It's all the same. I mean, unless you don't, my advice is if you have too many nodes and not many edges from a single node, maybe this is the way to do it. If you have a if you have too many nodes, but there is lots of connection between the node, then maybe matrix is the one way to do it. There might be other ways of doing it. You can actually implement your graph using a linked list, putting maybe dynamic pointers in it. I don't care. So there's another way of doing this too. 뭐 실제로 이걸 구현해도 상관은 없겠지? 그지? 이거 노드 하나에서 이렇게 구현해도 상관없어요. Up to you. Weighted graph. Like I say, if you just replace those values with the weighted graphs, and the weighted graph are represented with a simple extension of those used on weighted graph. Cost adjacent matrix representation use a matrix C just like the adjacent matrix representation just like did. I mean, instead of 0 and 1, you can start putting the cost between the vertices. Then you have a weighted graph representation in your data structure. So that's very simple ways of representing, accessing, programming your graph in your program your graph in your programs. Program your graph in your program. That doesn't sound right. That's how you represent your graph in your programs. Okay, that's the application of your data structure that we've been covered. In your books, they actually give a set of ADT graph. The function names are like a number of vertices, number of edges, exist edges, And they also give you some of the operations for ADT graphs. That's one possibility. If you already have a graph ADT, then you can certainly use it. Or you should be able to implement it yourself. Unfortunately, the book didn't give you those source code. I mean, it doesn't need. We know the very basics anyways. I'm sure you can do it yourself. Okay, so that's the end of this graph slide. That's chapter 16. Chapter 16, end of chapter 16. 17 is applications is no use. 다 했다. You're done. So I might not go into extra chapters. Instead, maybe we have time now, so I would start discussing about your final exams a little bit. Let me do a review of some of the chapters for your final paper. Final exam preparations. 오늘 되게 이상하다. 내 정신이 없다. Any questions on this part? No, yes, no. Okay, let me go into the final stuff. 나도 몰라. I don't remember all the questions in it. Let me take a look. What was the chapter that we covered in 어디까지였지? 미드텀이 어디까지 커버했지? 매트릭스까지 커버했나? 아, 스택 전까지. 아, 이것도 했고. Okay. So, what about the chapters before the midterms? There will be at least one or two questions will be asked from the chapters from the midterms. So I wouldn't say that you don't have to look at it, but more focus on the part after this stack. So maybe one or two questions from matrix or matrix은 물어볼 것도 없는데. Probably one or two questions from time complexity ones. Especially those ones that you have improving questions that no one actually cared to look at in your assignment. Maybe things like that can be asked again. So obviously I will ask you at least a few questions on the time complexity. 그죠? 그거 안 물어보면 what else I can ask? 뭐 마음에 안 들어요? Yes, there will be asked some questions from those parts. But other questions strictly are more focused on the second half of the course. Let's take a look. 나도 기억이 안 나서 시험지를 진짜 들고 왔어. 뭘 물어봤는지 안 물어봐서. Okay. So when we do covering the stack, the terms that we know, top, bottom. If you're having a difficulty memorizing those stuff, I usually ask to draw a graph like this. 그죠? Put it in, take one out from the top, stack, bottom, bottom. The terms usually used for push and pop, 그죠? Push and pop. In the textbook, they also use the same term for the Q, but I would suggest to use a term for Qs in NQ and DQ might be the better term to use. Don't get confused. So I might be able to ask you very basic properties of this pop. Of course, some of the problems that you can solve with this stacks, right? What was the problem that you can use to solve the stacks? What was the one or two example? Yeah, parenthesis matching. Towers of Hanoi is also one of them too, is it? Yeah. But it was involving a bit of recursive way of doing it. So those type of stuff. So I would recommend to 너무 많은 얘기를 하면 질문이 나가기 때문에 거기까지만 얘기하고 I would recommend to I would recommend to know the pseudocode level of solving those problems. Again, if I ask you to any programming questions in your exams, what I usually things that I don't care is what? I don't care about the syntax. As long as you can explain to me what you try to write is usually okay. But not like the last time. Last time I also said the same thing. I don't care about the syntax. So some people actually try to explain to me in the right there. 어떤 사람 거기다 문장을 이렇게 적어놓은 사람이 있는데 that's not acceptable. So pseudocode level of presentation would be great. Okay? If you can comply with the C or C++ coding schemes, then that's even better. Okay? So do take a look at those problems for the practice. LIFO, last in, first out. Don't forget to look at the definitions. I know English is not your strongest part, but usually I ask for definitions. 그죠? Do not draw this if I ask you definition of a stack. 이런 거 그리면 돼, 안 돼? 스택이 뭐예요? 스택의 property가 뭐예요? 했는데 이거를 넣고 푸시팝 이렇게 해놓으면 부분 점수 줘, 안 줘? 중간고사 때는 좀 줬겠지. 없어요. Review first. Stack is version of linear list. So stack Q, they actually try to give you the how to manipulate the linear list in different ways, where to read the values, where to not, how to manipulate the values within the linear list so they can act like a stack and queue. Stack, we know, first in, first out, push and pop operations. Okay. Stack ADT, empty size, top, pop, push. Can I ask you how to write down this ADT? Possibly. I can ask you some, but not very difficult ones. But there is more possibility that I might ask you how to use these ADTs in a given problem. Empty, return true. If stack is empty, return false. Otherwise, return the number of elements in the stack, return the top elements of the stack. So if you know their operations, then I don't think it's a problem. I think you can do it in quite simple ways. Top element on the stack, pop. Remove the top elements from the stack. So don't mix up with the top and pop. Top does not remove any of the values. Pop does remove the values. So if I give you a trick question, it's like can you use a pop to count the number of elements in the stack? Yes, you can. But what's after that? There's nothing left in your stacks. Is that something that you want? Push can be there as well. C++ abstract class stack definition in program 8.1. Yeah, why not? Do take a look at some of the programs that I said in here. You don't have to memorize it with your hands, but if I give it to you similar class definition in your exam, you should be able to read it. So do take a look at those programs too. 대충 눈으로는 한 번씩은 훑어보고 대충 이해는 하면 돼요. Inheritance? Probably not. 이거 뭐 top of stack length -1 element 0. Be careful about word. Some data structures start from 0 and 1. Depends on for their convenience, right? Be careful on that part. Be careful n-1 and that type of stuff. Some people complaining still. I know it's not a big deal. It's not a big deal. 뭐 별 크게 중요한 건 아닌데. What if I ask you how many elements in the given stack? n-1 will make a small difference. Be careful when you count those stuff. 미안해. 딱 찍어서 얘기해서 미안한데. 순간 정신이 나갔고 뭐 사실 걔는 뭐 n이라고 적거나 n-1이라고 적거나 사실 크게 대세에는 영향을 미치지 않죠. 네, 그래도 주의하라는 뜻으로 하는 거니까 만약에 그런 문제가 있으면 주의해서 하고 하면 돼요. 야, 이거 뭐 다 좋네. 프로그램 8.2. Because they use the array stack previous implementation of the array list, so it was much easier to implement this stack operations, small variations from those part. Any chapter that you should take a look at the time complexity of each operation that I ask you to analyze. That's the very basic part for. It's not just to stack, queue, everything, every data structure that I asked. So, parenthesis matching is the good example for that part. Will I ever ask you to draw this? Parenthesis matching, how to use a stack to implement this parenthesis matching. It was a very simple procedure, right? Once you have the empty stack, if you don't have the empty stack after all this, then you don't have the parenthesis, matching parenthesis. Your stack must be empty after reading all the part, right? 뭐였지? If you encounter right parenthesis, push into the stack. If you see a left parenthesis, push into the stack of the location of the parenthesis, and then as soon as you see the right parenthesis, you pop it out. We report the position of the right parenthesis with the position that is already stored in the stack. That was a very simple stuff to do. They even give you very simple pseudocode. Scan expression from left to right. When the left parenthesis is encountered, add its position to a stack. When the right parenthesis encountered, remove matching position from stack. It's very simple examples. So this practice ones, it's for the same thing. If you wanted to understand this program, you need to do it at least once anyways. Just follow your programs from top to bottom. So do take a look at program 8.6 and how they actually do it, what is the comparing conditions and stuff. Okay. 이 사람들이 큰일 날 사람들이네. 깜짝 놀랐네. And then Towers of Hanoi, problem 2. We understand the basic concept of this, moving everything. Now you're treating as one big part as another one. You have to move around the Towers of Hanoi, 3 different stacks. You can implement those things, right? We also cover a very basic recursive pseudocode for this Towers of Hanoi. I think I was writing down. Only takes 2 lines within the body. Within each parameter, you just divide it into first half, one disk, and leftover. You just find out which one is going to which stack, right? Different positions. And also given in your textbook as well. 그치? 설마 내가 이걸 그리라고 그러겠니? 아니겠죠? 물론 근데 공부할 때는 한번 해보면 프로그램 짜는데 도움이 좀 되겠지. See program 8.8 for Towers of Hanoi using stacks. Maybe I can ask you for why this time complexity is 2 to the n. What is the main reason for those parts? Explain briefly. I don't think I'm going to ask you how to prove it, but explain briefly. Just like your textbook explains in one small sentence. Okay. 모르겠다. I will continue to review on Wednesday. 수요일 날 계속해서 리뷰하고 나머지 좀 다른 거 또 커버하고 할게요. So I will collect the assignment. Thank you. These two, give your assignment to these two, and I will call the attendance now.